say what is the basis of analysis, and to get you an idea of why it is important to do what we are doing in this module, which is concepts and definitions, I just put up the thermodynamic definition of heat. Why? Well, what we are looking at is whether it was power generation, whether the aircraft engine, whether it's a diesel engine or solar thermal, somewhere we had this word heat coming in. So let's see what is the definition of heat when it comes to thermodynamics. This is a very fundamental and a very, very important thing, and one needs to be very clear about it. I've listed this here that heat is that form of energy that crosses a system boundary due to a temperature difference between system and surroundings. And the symbol is either delta Q or Q. And it is immediately tells you that all these words that I've underlined, what do they mean? What is the system? What is the system boundary? What do we mean by temperature difference between system and surroundings? So what is surroundings? And what do we mean by crossing? So we first need to develop these concepts. Only then we can appreciate what heat is. The second thing that we get to is that thermodynamics is the relation between heat and work. So while we define heat there, let's see what's the definition of work. And this could be correlated directly from what we get in mechanics as the vector product of the force into a small displacement, which would be that much work. In thermodynamics, you will find a definition which says that work is seen at a system boundary which has the sole effect of raising a weight. That means we are presuming raising of a weight means we are in a gravity environment, we are not in a microgravity environment where there is no gravity. And that raising of a weight means that there is a weight over there and you have connected it to something, and something is lifting it up and brings the weight over there. In this process, we assume that gravity is acting downwards. So if this is the only effect that happens at the system boundary, then it is work. So this is again happening at the boundary, and there are many other forms of work, but easiest thing to say what is work and what is heat is that if energy transfer across a system boundary is by any means other than by heat, then it is work. So this could mean that we are pulling a rubber band, that is work. Electric power, that is work, because we can then run an electric motor with it and do this lifting. This is what happens in the lift. So electricity is a form of work. Then you have stress or strain energy, like you have in a spring, or a rubber band being pulled, or a tire being compressed and expanded all the time when it moves, or surface tension effect, a film of something being pulled, or as happens in a reciprocating engine or a compressor, a piston which is moving inside a cylinder. So these are all cases which are associated with work. So before we proceed further, we first get some clarity on system boundary, and surroundings. So system is very simply that portion that we demarcate for our analysis. So what you can say is a space or a material that is of interest to us. So it's a very simple definition, and we are fully free to define a system boundary whichever way we want to do it. Interest means if you are asking a certain question or you want to know something about it, then you say, I want to know about that, so I must take that as my system. I do not want something about whom I am not interested to be a part of the system. And one can do this at a very large number of levels. The picture of a thermal power plant that you just saw, we can say that, well, here is a thermal power plant in which I saw some coal, and then there was a building which was the boiler, and then there we saw the turbine and a generator, and then on this side we had wires coming out, and we saw the switchyard. And so, well, if I want to analyze the power plant itself as a total entity, then we'll define this entire system. So this is my system, and then we say, well, what is happening in this power plant? And then when things become clear, that yes, what happened here was that coal went in, a railway wagon came or a conveyor belt came and it got coal into it and dumped it over here. And then we carried it into the boiler. Boiler, we burnt it, and for burning we needed air. So we got air into it. And then after burning, we threw the flue gases out. Flue gas is nothing but the term for exhaust gases, which is the combustion products that come out of a boiler. And we got work out as the form of electricity. And what we have not shown here is that there is a condenser into which we pump in water and warm water goes out. So together in this we rejected heat to the cooling water. So these three entities together became how much heat went in, and this is heat out of the system. So that is one example of a system boundary. The cylinder piston arrangement, you'll see that in many problems all the time. Say that that's a cylinder, and say there is a piston which is moving in it and it's completely leak proof. In practical thing, that's an idealization only. And we say, well, I want to study how much work I need to do on the piston, and I need to push this. How much work do I need to do so that it comes and moves into this position? So here, our initial system would be say, look, I want to know what is happening inside the piston. So there was some gas in it. When the piston was here, we say that my system boundary is this. It is just adjacent to the walls of the cylinder, but does not include the cylinder of the piston material, and it is such that it includes all the gas which is contained in this device. When it gets compressed, the system boundary comes over here, and we now have this system. What happened? The system changed its shape, the system changed its size. That is okay. So that's another example. And what we do is, when we have defined this, we say that this is the material of interest to me. So this is the system. Everything, and then this thing is the system boundary. And everything else outside the system boundary is the surroundings. So we've got three important things coming up here, that we defined a boundary. And what is the boundary? This is actually a three-dimensional closed shape. And this could be real or hypothetical surfaces. And if the picture does not convey the full meaning, it is, we can always write down a few words and say the system contains this and it does not contain this. So we are always free to write that. So we are absolutely clear what is in it, what is not in it. This is the first step in analyzing anything, and we'll take a few more examples to illustrate this point. It's not just related to thermodynamics, but to many other things as well. Say we take a hydroelectric system, we have built a dam, and this is the ground, and there are various rivers coming into this, and water being let out of the dam or being put out by the hydro generators. So that's the level in the reservoir, and right now everybody is monitoring the progress of the monsoon. So everybody's first thing is, how are our reservoirs doing? And you'll routinely see such information in newspapers and say, well, look, what is happening in my reservoir? So you say, well, I'll take my reservoir as my system, and I define the system boundary like this, and rainfall is coming, that is falling into it, rivers are draining into it, that's okay, and what is going out is here and here. So with that, we can then do a balance on this and say, will this level go up or level go down? So that's the analysis that one does. And this is pretty much similar to the analysis that you would do with your own bank account. So how much money did I put? How much balance do I have? How much have I expended? So the system and this way, its analysis, you have to clearly define what is it that you want to study, what is included in it, what is not included in it, and then we can proceed to do all the other things that we learn in the next modules, answering different questions related to the performance of the system. So this is what it also means is, when we show the system boundary, we need to make a sketch. Sketch doesn't have to be a very, very good thing. You can make a freehand sketch and say, look, this is what it is. And the picture should actually convey some sense of what that device is all about. Some typical pictures that are symbols that are used, the turbines that we saw in those photographs are shown with this picture, with this symbol. Because steam goes in at one side, expands and gets bigger, whether it was a gas turbine or the steam turbine, the same thing happens there. And what happens in this is that we have steam or gas entering over there, and the steam or gas exhausting there at a lower pressure and a lower temperature. And you say, look, I need to analyze this system. I want to know how much power it produced. So when this happened, the rotor got power and it produced work which came out from the shaft as work output. So if you want to analyze this, we want to write the various laws for it and then put properties on it and do a calculation. The first thing is we say, look, what is my system that I want to study? And what one can do is say, look, this is my system boundary. And the system boundary includes the complete turbine casing, the photograph that you saw, but excludes all the metal inside this turbine. So so only thing my system includes is steam. So we say here system is this, but excludes all metallic parts. And includes only the working substance in it. If it's a steam turbine, it could be steam, or if it's a gas turbine, the aviation engine that you saw, that would be gas. So now we become very clear that, look, what is it that I am doing? Whose properties do I need? Which laws do I need to apply? Then it becomes clear. The need for system arises from a very, very fundamental thing about all study, is that the laws of nature, say laws of physics, which could be the laws of thermodynamics, the laws of motion, electromagnetics, all these laws are applicable only to a system. If we are not clear what the system is, we are very likely to make mistakes in applying the law and get some very erroneous results. So this is a very, very crucial thing, both as a requirement here as well as a scientific requirement, that one can apply laws of physics only to a well-defined system and you say what is in it and what is not in it. So that was the first part about the system boundary, and the surroundings. So the system boundary we show by dotted lines, as I have shown here or here. We write down what is in, what is not in. And then the question is, what happens to the system here, here, and here? Okay, so what is happening here? In reality, there is a pipe. And there is a pipe connected here. Through which something is moving and entering the system boundary. So this is a bulk material, steam or gas or say even water. This is moving and we made a system boundary here which is a hypothetical surface. A surface which cuts the pipe, but really there is no surface inside the pipe. So it's an imaginary surface that we have created, and across that we have seen things moving through it. So it's like saying that this is my hypothetical surface, this is my pipe, and through this, whatever is the substance that was flowing, that has moved. So this was a little element of, say, the steam or the gas. This element moved in and crossed this thing and came in here. So that's a hypothetical surface at this point. What about the work output? This is a solid shaft, metallic shaft, which is turning and causing a torque to work against the magnetic field in the generator. So this is the generator. We've now done the same thing, but instead of a hypothetical surface in a gas, we are now going to say I'm going to have a hypothetical surface which cuts the shaft at that point. So it is an imaginary surface across which you can then see this particular part turning and producing a torque. So there again we have a hypothetical surface there. And that completes the three-dimensional closed system. We are not showing the other two dimensions, it is much too complicated. But suffice to say that what we mean is that this is a completely axisymmetric machine, and we have put our system boundary all around that machine. Okay, so now what happens if we don't follow this? We take the same example of, say, the turbine. There is power there is steam or gas going in and steam or gas coming out. So what I explained here about going into the system, the element, if it is moving out, the same thing, it is out of the system. In a minute we will come back and re-look at this again. So this is now saying, look, I want to understand what the steam is doing and how much power it is producing, or the gas, how much of the gas flow is taking and what thrust it produces, things, questions like that. And somebody says, okay, fine, I need to draw the system boundary, I'll make a system boundary. And they make the system boundary. The problem is, you have unnecessarily conveyed a meaning which does not intuitively say that, look, I'm looking at the steam inside the steam turbine or the gas inside the gas turbine. This depiction shows that this material over here is also included in the system. And what is this material? This is the surrounding air. And what is this? The metal is there. So we have to now write that it excludes not only the metal, but also excludes all the air around it. All that we have done is we have added unnecessary complication to this. So it is best practice that we be very tight in defining what the system boundary is and avoid such a thing. Same thing with the cylinder piston arrangement, because this will keep coming back in the course many times. If the piston is here and you want to study what is happening to this, and somebody draws a system boundary which is like that, again the same problem. We want to know what happens inside here. Just let us restrict to that only and not worry about this air or something over there. These are of no use to us. We don't want to study that. So we go back and say, well, the right system for this is this one. And system boundary we always will show by dashed lines. And what this dashed line means, it is that this boundary is either the real surface or a hypothetical surface just a few nanometers outside the surface, does not include the surface, but includes every molecule which is there inside the system. That's our definition. So this is the depiction of the system boundary. The next thing we will do is something we looked at in this example of the turbine. Okay, but before that, let's go back and say, look, what did we write about the definition of heat? That form of energy that crosses system boundary due to temperature difference between the system and the surroundings. So now we know that I have defined my system based on what I am interested in. We made a boundary. We showed a symbolic way what the boundary is, what is included in the system, what is not included in the system. So that gave us clarity on what is surroundings. So now we are clear that, okay, these words I have understood. The question is now, what is mean by temperature difference? So here, now that we know that there is a system boundary, what we can say is, if this is the system boundary, I am just drawing in general something. This is the system, this is the surroundings. Then, if there is some temperature here and a different temperature over there, energy transfer takes place over there, that is heat. And that we will denote as crossing the system boundary and call it Q or delta. We are not worried what is the mode by which this heat transfer takes place. It can be radiation, which does not require a medium, which means that, say, like the solar collectors, we make the solar collector as a system boundary, then sunlight enters that system as radiation. It could be convection. Say you have a hot material sitting in the table and it is losing heat to the surrounding air, so the air is coming and flowing past it, and by a combination of conduction and convection in air, energy is transported across the system boundary. That is also heat. Or it could be by conduction. For instance, we have a large body and we say, look, I want to know what happens in this part of the body. So this is the system boundary, and there is conduction taking place maybe there and there. So that is also Q. So these are the only three ways in which, if energy transfer takes place across the system boundary, we call it heat. What it means, the body never contains heat. That's one implication that has come out from what we have now argued. So heat cannot be stored. Same way we can see that work cannot be stored. These are properties that occur at the system boundary only when the system and surroundings interact with one another. To say that a body contains heat or the heat energy of the body changes, these are wrong statements. We will never say this type of a thing, that body contains heat or its heat energy goes up. Never to be said. But in thermodynamics, heat is a transient phenomena. observed only at the system boundary. And that's what this definition is so important. Now, okay, so let's take one more example and say, well, is that heat? So we have a pipe, and in this, say we are pumping in hot water, and outside the pipe, we are blowing air. It could even cold air, cold water, and that's how your central air conditioning systems work. Like in a pipe, you have cold water flowing in, and outside you have warm air coming in. In your window ACs or your split air conditioners, you have a very cold gas that is flowing through this, and as air goes over it, the air gets cooled. The temperature of the gas as it goes through keeps increasing. And we say, well, this is my system boundary, and I want to study what is the amount of energy transfer that takes place. And somebody says, well, because this water or the gas is flowing in, there will always be an element here, say this element, which got pushed in because it is flowing, and it crossed the system boundary and entered the system. And at the other end, this element exited the system. This could be an element 1 millimeter on the cube, or if it's a very big system, even could be 10 millimeters, or in a very small system, it even be, say, 1 micron by 1 micron by 1 micron. So put a real number on it. So somebody says, this thing had its own energy and it went in. So there is energy transfer across the system, and that is heat. Now that is, neither of those are correct, because heat, as we have seen, it happens only because of temperature difference between this and this, whereas this is not because of temperature difference. And we'll see later on whether it is work. There's a slightly different definition here, that if we define the system in a different way so that it includes this element, and then we push the element to change the system boundary, then there is work done on the element, otherwise not. So this is not heat transfer into a system. But having said that, we now get another important definition coming up, which is that if this does go in, what do we call it? And that brings us to the idea of a mass inflow and mass outflow. So first thing we do, we define the system and the system boundary. The second thing we got to do is see where is heat, where is work. Next thing we do, where is mass inflow, where is mass outflow. So what we do for this is what we have seen just now in the example of the pipe. A bulk material moved across the system boundary. This is mass inflow. And if another element or something, this water continues to flow across the system boundary, that is mass outflow. So we need to look at the system, and the way we define the system boundary will define what is mass inflow and what is mass outflow. Let's take the example of an LPG stove. So you have a burner in which there is a hole. There are many holes there. If you look at a burner, it looks something like that, with a lot of holes there, and on the other side there are more holes. And what happens there? If I take one hole there and make a section, here we are pumping in the gas fuel, which is either LPG or natural gas, plus air. And what it establishes on top is something that looks bluish white. That is a flame. And we ask, what are the mass inflows or outflows in this flame? And so the thing to do is what we have done so far. We said, well, I must take my flame as a system and define my system boundary. So we say, okay, the visible portion of the flame is my system boundary. And we say, now, what is happening in this? Well, you've got gas coming in, cutting this hypothetical surface of the system boundary and entering this, exiting the hole. So for us, this gas plus air coming in is mass inflow. And after it comes in, it burns, and all the gases that are leaving out here, this is mass outflow. So that way we look at every system and say, is there mass inflow? Is there a mass outflow? In the case of the cylinder piston arrangement, we just took that, say, air in this and moved the piston there and brought it there. So in the first case, if you say, or in the second case, we define the system boundary there. So in this system boundary, there is no mass inflow, no outflow. In another case, say a tank into which water is being poured in, say water is being fed into this, the level of water initially was there and it keeps on rising over there. And we say, well, I want to study how much water level is there in the tank and how is it changing. So you can say, well, my system is the space inside the tank, but include only the water, not the air. So we have to write that there, only water. And there is water being thrown through this, so there is a mass inflow into this, but there is no mass outflow. So there is inflow, no outflow. So that's another example where here you have no inflow, no outflow. Here we have inflow but no outflow. You can modify this one to remove this and say, well, water is draining out of this. And so you have outflow but no inflow. And we saw this example of water flowing in a pipe, or now as we have seen this turbine or in an aircraft engine, you have both inflows and outflows. So that's the next step. System boundary, surroundings, system, work, heat, mass inflow, and mass outflow. Now, based on this, we will broadly classify systems into three types. And in a way, this will also give us the foundation to decide on what strategy to use to write the equations of this problem. So, we define a system as isolated if it has no interactions with the surroundings. When we say interaction, we have included both the terms that we have so far defined, that across the system boundary you have interaction in the form of mass outflow, inflow, and energy as heat and work. So that's the system that we draw. Then we say, well, is there mass inflow? Yes or no? If so, where? Is there mass outflow? Yes or no? And if yes, then where? Is there heat? That is energy transferred due to a temperature difference? Yes or no? Then put that. Work, that means the system boundary is moving against a restraining force through a distance, that is work. That could also include electricity. We say yes or no and then show it. If the system has none of these, it is an isolated system. The system is closed system if it has mass outflow is no, but energy is yes. So the example of the cylinder piston arrangement again comes back. Easy to see that. So the system, say this is gas, say in the say a diesel engine, this is hot. Around this you have water going around it, so it is cooling it, and say the gas is pushing the piston that way. So if you want to know what is the relation between the position and the work done by this, the first thing becomes that we define our system over there. This is the system boundary, and then we say, well, what's happening? There is no mass inflow, there is no mass outflow, but there is water here which is cooling it. So across this there is heat transfer, and as this system boundary is being displaced against a restraining force, this side there is work. So this system is classified as a closed system. And the third type of the system is open system, which has both mass inflow, outflow, either of them, and energy. When we say that closed system has energy transfer across the system boundary, it could either be heat alone, it could either be work alone, or it could be both, or it could be heat at multiple places also. So that's fine. Only one of that condition is met, that's okay. In open systems, there has to be either mass inflow or mass outflow, or both, or more than one of each. If any of those conditions are met, then we say yes, there is mass flow across the system boundary. The same thing with energy, the way we looked at a closed system. That if they got either heat or work or multiple things of that across the system boundary, then there is energy transfer. Then it becomes an open system. Okay, so that brings us to the next most important thing, that having classified systems in this way, it now gives us a basis for using two terms which are fundamental to deciding which equation to write for the conservation laws. And that is here. As isolated system, there is nothing to understand about it. And there are internal changes taking place, for example, but that's a different thing. If it's a closed system, there is no mass transfer across the system boundary, and say, which equation should I write? Then we say that we will define the system boundary such that the system includes all the material or the mass which is of interest to us. It is not, nothing is being added, nothing is being removed, and so we say that we have controlled the mass on which my analysis will be done, and that gives us the control mass approach. So essentially, control mass is telling you that we are dealing with closed system. And all the mass that is there in the system, or the material or the substance, always stays in the system. So there is no addition, no removal, and the shape and size may change. Shape, size, or both may change, But the mass that was there, that does not change. The same amount of material is always being tracked. Okay, so that gives us the idea of a control mass approach. And when we solve problems later on, having defined the system, we come to this point. We said, look, this is a closed system. This is my mass of interest. We got to use the approach, which is the control mass approach, or CM. What that does is it gives us equations in a particular form, and we can solve those equations quite easily. The other case where there is an open system, what we do is we fix the volume in space, thus fix the system in space. So it was the example of the turbine. There's a pipe here through which steam was flowing in, say steam going out and work being produced over there. We define the system boundary by this. And now we say that there is mass entering from the system boundary here, mass inflow here, mass outflow there, and work outflow there. So what have we done in this system? We said, look, my system in this case is going to be fixed in space. This system will not change its shape, will not change its size, no matter what happens. This mass flow rate can increase or decrease or may even become zero, doesn't matter, but my system is going to be this. What we have done is defined a volume, a three-dimensional space, closed space, by the way, which will not change with whatever happens across it. So this system boundary is denoted as the control volume, CV, and this will be the CV approach. And so in solving problems, we will make this, and instead of writing this as a system boundary, we will then say that this is my CV. And in this case, we will say this is the CM. Once we reach this point, we will have enough clarity on which equation to use. Okay, so that's how much I will cover today. I will stop now and just give a summary of what we have done. We started off by looking at some applications, and in every lecture I will keep showing some more applications of the real world. And we got a feel of what is the connection between thermodynamics and those things around us. Very, very crucial things like using electricity, generating electricity for our use, and we cannot escape the fact that these have environmental impact, and we have that is now driving our concern on what we need to invent, what we need to develop, and how we need to use quote unquote energy. So we saw some examples from aviation, from desalination, and all of these produce quite tangible benefits for society. Then we asked ourselves the question, how can I analyze this? How can I study this? And we said, look, first make a sketch. Try to make it as well as you can, trying to replicate what the real thing was. Some semblance to reality, you can call it that way. Then draw the system boundary. That will tell us what is the system. If you need to write a few words, write that. It will also tell you what is surroundings. Then we said, can we identify, we defined what is heat as that form of energy that crosses the system boundary because of temperature difference only. And then we defined work as energy across the system boundary that causes force into displacement or lifting of a weight or any other form of energy but not heat. Then we said what is mass inflow, what is mass outflow. Based on that, we defined systems as isolated, closed, or open. And finally, we said that if it's a closed system, we fix the mass, and the approach that we will use for equations is the control mass approach. And for open systems, we define a fixed volume as a system boundary and use the control volume approach. So we have come up to this point, and we'll continue this discussion next as to what is the system, how do we characterize it, how can I put numbers on it, all those things, and we'll take it now. Tomorrow we'll come back on this. Yes.